All right, let's just jump right into it. Today we're talking about something that might sound a little awkward, but is, from a biological standpoint, absolutely fascinating. And that's the science of semen liquefaction. You know, biology can be pretty wild, and this whole process is a perfect example of that. So, what's the big question we're trying to answer here? It's really this. How, and maybe more importantly, why, does semen go through this dramatic change in consistency right after ejaculation? It's a transformation that is, well, pretty crucial for the continuation of our species. So, you've got this initial state, right? It's thick, it's viscous, almost gel-like. But then, just a little while later, it completely changes. It becomes thin and watery. Now, this isn't just some random thing happening. It's a very precisely choreographed biological event. So let's break down how it all works. To really get why the solution is so brilliant, you first have to understand the problem. So let's start at the beginning, with that initial sticky situation. Okay, so right after ejaculation, semen has this consistency that's a lot like pudding or maybe even jello. It's thick, it's coagulated, which, when you think about it, seems kind of weird for something that needs to travel, right? So, why is it a gel in the first place? Well, it all comes down to these specific proteins called seminogellins. They're produced in the seminal vesicles, and their whole job is to create this thick, gel-like trap that basically holds all the sperm in place. But why would you want to trap them at all? And that leads us to the next really crucial point. This gel, while it does have an initial purpose, very quickly becomes a major obstacle. It's something that has to be overcome for the sperm to complete their ultimate mission. I mean, at the end of the day, a sperm's one and only job is to travel. They are literally built for motility. They have to move, they have to swim, they have to navigate a really long and pretty challenging journey. And this quote just nails it, doesn't it? It perfectly illustrates the problem. Being stuck in a thick gel is the exact opposite of what they need to be doing. They can't just hang out like marshmallows and jello. They've got a very, very important appointment to get to. So the body needs a way to set them free. And this is where the story gets really good. This is where our hero enters the scene. So let's watch how this little biological drama unfolds with the arrival of one very special enzyme. Okay, so if the sperm are all tangled up in this protein net, how in the world do they get out? What's the key that's going to unlock this biological cage? The answer comes in 3 simple letters: PSA. This is our superhero enzyme, and it is about to change absolutely everything for those trapped sperm. Now, no, we're not talking about a public service announcement here. PSA actually stands for prostate-specific antigen, and scientifically, it's a type of enzyme called a serine protease, which basically means its one specific job is to go around and break down proteins. The best way to picture PSA is as a pair of microscopic, incredibly efficient scissors. Seriously, they are these little precision tools designed for one single purpose: to cut up the protein chains that are holding that gel together. So our hero enzyme is on the scene, which means it's time for the main event, the great liquefaction. Let's take a look at exactly how PSA gets this important job done. The process itself is actually beautifully simple. First, PSA hones in on its target, those seminogellin proteins, the glue we talked about. Then it gets to work, snipping and slicing those protein chains into lots of smaller pieces. And what happens next? The whole gel structure just collapses, turning from that thick goo back into a liquid. And get this whole incredible transformation doesn't even take that long. Typically, from start to finish, the entire liquefaction process is done in about 15 to 20 minutes. That's it. And the result is, of course, what this is all about. With that gel completely dissolved, the sperm are finally released. They are now free to start their epic journey, swimming like little Olympic champions toward their final destination. It's also worth pointing out that PSA isn't a lone wolf here. It's definitely the star of the show, but it has a support team, a whole demolition crew of other enzymes like human kallikreinin 2 and KLK14 that help break down that gel super efficiently. So we've seen how this really elegant system is supposed to work, but what happens if it doesn't? What are the consequences when this crucial process goes wrong? Well, if liquefaction doesn't happen the way it's supposed to, the consequences can be pretty serious. The semen just stays too thick, too sticky, and that means the sperm stay trapped.
If they can't move, they can't do their job, and that can have a huge impact on fertility.
So, why might this fail? There are a few medical reasons. It could be things like infections in the prostate, which is where PSA is made, or maybe blocked ducts that stop the enzyme from mixing in properly. And sometimes the body just isn't producing enough of these critical enzymes to begin with.
And this really brings us to a key takeaway. A lot of us have probably heard of a PSA test in the context of men's health or cancer screening, but it is so much more than just a number your doctor looks at on a lab report. It's a microscopic workhorse that is absolutely essential for the very beginning of life.
So, to wrap this all up, let's just end on this thought, because it captures everything we've talked about perfectly. Biology can be a messy, sticky business, but thanks to enzymes like PSA, everything flows exactly the way it's supposed to. Science really is sticky until PSA shows up.